I'm going to talk about a different topic. It's about spectroscopy, but it's about metal ions in biological systems. And this is super nice, this topic, and I hope that you like it. So, I'm talking about spectroscopy, study of metal ions, and a journey through the chemistry of copper. So, obviously, you remember the periodic table, and the table of the elements, in this case, is based on their abundance in the hard cross. And if you can see some metal ions or metals in different oxidation states are present in the cross, and it's very important to know how copper is interacting with the different proteins or in a different way. Metals are involved in metalloproteins like manganese calcium cluster. I'm pretty sure that you know this kind of metalloproteins. For example, this manganese calcium cluster is involved in the oxidation of water during the photosynthesis, and it's nice to know that it's a form of cube. And another example is iron copper center, and you have iron in your blood. In fact, that's the reason that our blood is red. So the mosaic in copper is another example of how the metal is involved in this metalloprotein. So it's important to note that viability of these metals has often been given the reason of these choices in proteins and in hormones and different biomolecules. This is just an example. This is just about examples about different metalloproteins. For example, a superoxidase dismutase that is important to dismutate this kind of compound of the molecule of the oxygen to a different molecule of this and obtain oxygen, of course. And this is just an example. And it's important to note that the metal ions also play structural. It's reverse. Play a structural role in various biological systems like zinc fingers. The zinc fingers is protein domains that bind into the DNA, and the thermolysin is another protein that involves zinc like a catalytic side, but it has calcium, but this calcium is just structural for the protein. So I wonder if some metal ions provide this structure and to the proteins, how the metal ion can provide a structure and the reactivity to the protein that binds them. So this is an example of the case of the copper. Copper is super nice. It's my favorite metal ion. And it's a copper is oxidase copper 2 to copper 1. And in this case, copper is so reactive. But the copper is binding to a specific site of the protein. For example, the amino acid histidine is the favorite place to bind copper. And always we think that another kind of amino acid is involved in this coordination sphere, like the methionine, cysteine, or maybe the backbone amide. So this is just an example that the copper is binding to a prion protein, and it is binding with 4 histidine, and this is important because is changing the structure of the protein, and the bad protein, because the prion diseases are so bad. But here, maybe the copper is just giving the structure of this protein. So what are the strategies to study copper? And it's nice to explain some spectroscopy. I'm pretty sure that you remember how spectroscopy works. So if you remember the molecular orbitals, you have different electrons in the sphere, in the metal or the ligand, and you can see the jump of this electron from ligand to metal, or in metal to metal, for example, the DD bands. So this characterization is important because we try to know with UVB absorption or circular decreasing to understand how copper is binding and how copper, the electrons are interact with this with the ligand. In fact, circular decrease is very important because it's we have a lot of information about this technique. Electromagnetic resonance, we explore the electronic spin, the properties, and it's super nice. Nuclear magnetic resonance too, we try to understand how nuclear spin is binding, or how is perturbed the environment around the spin nuclear of different elements. X-ray absorption, and X-ray absorption is with high energy, with synchrotron energy, and it's very important because we can check the geometry of the complex, oxidation state, coordination environment, and it's important because it's you put the metal and how the atoms are binding to the metal. And another example of spectroscopy is ICP, OS. In this case, it's a general method that detects metal ions. In fact, detection metal ions, but we don't know the oxidation state, but we can see the different elements inside the sample. This is an example for hormones. Hormones are in different parts of the organism. In this case, we can check the glucagon and GLP-1. Glucagon and this GLP-1 are glucose regulatory hormones, but it's interesting because copper and its accumulation in blood has been associated with different diseases like diabetes type 2 and type 1. And we wonder what happens if the copper is binding to this site. And we see the EPR and XIS. We can see that this is just a titration of different equivalents of the metal, and we can remove information about this spectra. So we can propose different models how copper is binding around the hormones. Another example is gamma G crystalline. Crystalline is a protein involved in the cataract disease. In this case, copper ions bound to the gamma crystallines, and then we have a reduction of copper to copper 1 and a formation of free radical. This is a very important process. In fact, we can check the different mechanism or aggregation because if you remember, the catharaces are composed about different proteins aggregate inside the lens. So we can check the mechanism that the copper is accelerated maybe the mechanism of aggregation of these proteins. So it's important to know that this protein could act not only as structural proteins, but also as key players. Yeah, thank you. Thanks. For metal and redox homocysteine. This is again the brown protein. In this brown protein, we use different spectroscopy like UV or CD or NMR. In fact, here we use NMR to check. If you remember, the histidine has 2 nitrogens, and each nitrogen is so different. I think if you think about this histidine, so we check how copper is binding on each for each nitrogen, and then we check the pKa value of the complex, because sometimes we are in the middle, or we are in the pKa of the complex. So we are pretty sure that 7.4 is only a pH. We have just one species and know that a mixture, and obviously propose different models. And peptide amyloid is another example. In fact, here we can check the differential potential of the copper 1 to copper 2, or copper 2 to copper 1. And this peptide is involved in Alzheimer's disease. So with this part of amyloid beta or prion protein, and how copper is binding binding to each atom, we can propose a design of bifunctional tetrapeptide against Alzheimer's. So we build a tetrapeptide that involves binding copper and modulates the aggregation of A beta. In this case, we check different techniques, not just the spectroscopy, and in fact we do this assay with the brain blood barrier, and a different localization with the NMR, NMDR, the receptor, and a different parts of the work. We can propose this part, this bifunctional tetrapeptide as against this disease. And then a take-home message. I think the first one is the more important: the viability of these metals, along with their redox potential, combination possibility, and dynamics, determine the specificity of metals in biological process. This versatility of the metal ion to form a stable complex with hormones, proteins, and peptides. It's important. And this spectroscopy approach underscores the importance of having continuous feedback between biophysical, these techniques are biophysical, and biological studies to design optimization of metal targeting drugs. And that's it. I am postdoc of Liliana Quintana in Simvestav Zacatenco, Simvestav Química and Chemistry, and Simvestav Centro de Investigación sobre el Envejecimiento. So this is the team, and this is Liliana. You only know here. So thank you very much.
Thank you, Carolina.
Thank you, Carolina. So, one of the things that I'd love to do would be to use the metagenomes that we have, like from the different layers of life.
Yeah.
And maybe do like Luis do propose models for the main enzymes involved in the processes, of the different metabolic processes in the different layers. Do you think we can sort of like map them to particular enzymes, the particular metals that are needed for each of the main enzymes, to also have an idea of the abundance of the metals, how life really made use of abundant metals? I mean, like copper was something that came later in evolution. But so what was first? I mean, can we see an enrichment of some enzyme because of this evolution? Or do you think that approach is possible?
Yes, in fact, yeah, because I think it's difficult because it's a lot of work of extract the protein or extract each protein.
Just conceptual. Just think about it. I tell you this, and we have this enzyme.
And
you tell me what metal I need for that enzyme to work.
Yes, because sometimes metal is the behavior of the metal depends on the geometry around, and sometimes the enzymes or proteins are fold, or it has the structure, a particular structure to take the zinc, for example, in a tetrahedron geometry, for example, or copper in the square planar geometry, no, or iron in a different in octaedric form. Yes, obviously, and it is super nice. This part of the chemistry behind the metal ions in a biological sense. Yeah, thanks.